So we've got a lot of talks today at Big Tech Day about AI, in case you hadn't noticed. A lot of talks about how you use AI, what it's good for, and I think now we'll be hearing a little bit more about the actual running and the infrastructure. We'll be hearing a little bit more about the infrastructure and how you actually run these things, and especially if you've got the very real concern of data privacy, data security. So we've got three experts from here at TNG to tell us about that, and maybe I can briefly introduce them. So Fabian Roll is a software consultant here with a mathematics background, who's been really running our GPU cluster and developing it over the last couple of years, and who's also then recently been kind of the driving force behind the project that we'll hear today. Marcel Lippmann is senior consultant here and has really gathered a lot of experience over the last however many years at TNG in various client projects on topics like software architecture, DevOps, cloud, and I think especially a lot of very practical experience really running Kubernetes clusters and running platforms on them. And Marcel originally had a background in computer science, but we're an equal opportunities employer, so of course physics is also represented here. Be glad to hear. Benjamin Merkel is principal consultant here, and after a career in quantum optics, came to TNG to also run our GPU cluster, which he's been doing for the last couple of years, and I think really growing it massively as well. And as part of that was really specialized in the optimization of some of the models that were running on that cluster. So many thanks, three of you. Just leaves me to say the stage is now yours.
Thank you. For the last 3.5 years, we have been building our own GPU cluster at TNG. Today, it has grown to more than 100 GPUs that we all manage ourselves. This cluster is the basis for our in-house AI services. Services like LLMs, vision, and audio models. Models that we can use with confidential data. Data that must not fall into hands of third parties. And this is really the key motivation for building our own cluster. Since we own the hardware and we maintain the entire software stack, we can ensure that no input or output data is logged, stored, or reused for training purpose. This is not only relevant for services that deal with TNG internal data, but it also enables hundreds of colleagues to use TNG-hosted LLMs as productivity boosters in customer projects. These tools include Taya, the TNG AI assistant, a tool much like ChatGPT, but with a fully private mode. And other tools are coding agents, such as OpenCode, which has become the #1 use case at TNG. But at TNG, we also do research in AI. In particular, last year, we released 2 successful Chimera models with more than 600 billion parameters. That's quite large. And we're also exploring methods of fine-tuning and training new models. And while we already own a lot of GPUs, model training is very demanding on resources. And that's why we started renting more hardware. This one is a rack with 8 nodes fully equipped with B200 GPUs. This is a different class than the H100, H200, and RTX Pro GPUs that we own. This single rack alone has more resources than the entire TNG-owned infrastructure. And it's highly valuable for research. And in fact, today in the morning, there was already a talk about research that we do at TNG that we can do on this particular cluster. And also, there's a showcase down there where you can also talk to colleagues about the research projects. But today, we want to focus on inference. What about inference? TNG promises the highest data privacy for LLM inference on our own hardware. But this is not our own hardware. We do not control the provisioning layer. So how can we ensure confidentiality? How can we ensure privacy? In short, we can't. We do not trust the servers And therefore, we strictly separate any confidential traffic from the AI services that run on those rented servers. But the question, of course, remains, how can we build a system? How can we develop trust? How can we ensure confidentiality on systems that we don't own and not fully control? And this question is actually very similar to a problem that many people face with cloud services in general. So cloud services offer very attractive features like high scalability with very little maintenance. But of course, the underlying problem is that technically, the cloud provider can always somehow read your inputs and outputs. And of course, you can make contracts and get the provider to promise, oh, we won't read your data, but there is no technical guarantee. And in this talk, we want to change it. We want to discuss how is it possible to actually enforce confidentiality on a technical level. This goes beyond the promises that cloud providers could make. This is really a guarantee.
So now we've understood why we are interested in confidential computing, but let's take a bit of a dive and understand what we try to protect exactly. Data typically comes in 3 stages. So first of all, there's data in transit. We rely on this every day. So for example, today when you open the big Techday website on your phone, you trust that this connection is secure and protected. Then there is data at rest. For example, when I save a secret on my laptop, I trust that it is encrypted and no one can steal it. But there's actually a third, there's data in use. So for example, when you send an LLM request to a server, then inside the CPU memory and GPU memory, this request is unencrypted and vulnerable. And this is where confidential computing tries to close the gap by protecting you from a potentially malicious hypervisor or host system like the B200 cluster Benjamin talked about. So what are the actual confidential computing solutions we want to talk about today? So first of all, there's Intel Trust Domain Extensions, short TDX, which has been generally available since 2023, and it encrypts and protects the CPU memory like depicted here on the right. Now, one thing you want to also notice in the picture is that this Intel Trust Domain Extension is not a technology you just enable on the host, but you need a virtual machine on top of that, which is then called a confidential VM. And just one side remark, so you know that, so you see that this is actually very recent and still under active development. I want to mention that last month, the first long-term stable Ubuntu version has been released that natively supports these Intel TDX features. But we're not just interested in CPU levels, but we are mainly interested in GPUs, and there's a corresponding technology from NVIDIA called NVIDIA Confidential Computing, or NVIDIA CC for short. It has been generally available since 2024, and it encrypts and protects now the GPU memory, as you see here on the right. Now, at the beginning of this year, also a major improvement happened that regards NVLinks. NVLinks, as depicted here, are fast interconnects between GPUs that you want to have in order to be able to serve large language models in a very high-performant way. And what happened at the beginning of this year is that now also this NVLink is part of this NVIDIA Confidential Computing solution. But wait, the virtual machine protected by these confidential computer solutions, they still live on these untrusted hypervisors. So did we just trade now one problem with another and still haven't gotten any better? Well, with this solution alone, we haven't, but there is another ingredient to the recipe, namely there is remote attestation. So the fundamental idea is that these solutions that provide this encryption of RAM and VRAM, that they are also responsible for vouching for the integrity of this workload. So here on the slide, you see how this works on a high level for Intel TDX. So in your confidential VM, you first want to create a fingerprint of the VM that encodes information about the config of the VM, runtime measurements, and so on. And the crucial part then is that the confidential VM signs this fingerprint with a hardware key. So this key is not in software, this key is really in the hardware inside the CPU. And this hardware key is not there on its own, but it also comes with a certificate chain of trust up to a root certificate of Intel. So now you have a fingerprint, a hash of your VM, and what you can do is you don't just leave it in the VM, but you can send it in your remote trusted environment, like on our servers, your servers, servers of your clients, and can verify that the VM is actually what it claims it to be, and only then you can say, okay, now I trust this VM. So what is the upshot? We no longer have to trust the host system, but we trust the hardware, we trust the Intel CPU and the NVIDIA GPUs, and so the trust shifts from the host to these technologies, and in the end, the trust shifts to Intel.
Okay, what do we need in order to actually build and launch such a confidential VM? Of course, we first need some hardware. We need Intel processors that actually support this TDX feature. And this is the case since the 5th generation of Intel Xeon processors. But this is not sufficient. Having a processor is not sufficient. You also need a specific symmetric RAM distribution, which means here you can see a configuration where you need 16 memory sticks, and actually you have to populate every memory channel on the main board in order to really start a server that supports TDX. So that's a quite special requirement, but it's doable. Of course, you also then need GPUs, and we already have our GPUs in the remote cluster. We have B200 GPUs, and this is very fortunate because this is, as Fabian already said, the first GPU model that fully supports protection at NVLink level. So not only the data inside the GPU VRAM is protected, but also the communication between different GPUs on the same server is protected as well. Now we have the hardware. How do we build and launch the VM? Building and launching a confidential VM is very similar to starting a regular VM. And if you are familiar with virtual machines, you might recognize commands like QEMU system. And it works pretty much the same way also for confidential VMs, for TDX VMs. Only that you have to pass specific arguments. For example, you can see you have to specify something with the memory. You need to tell the VM which type of memory it should use and provide as encrypted memory inside the VM. And the second argument also indicates there's something happening with the quote generation socket. That is also very critical because it enables the VM to issue a cryptographic proof of its runtime integrity. So this cryptographic proof that also Fabian already mentioned is also called quote. And this is really the behavior, the method how you enable the VM to issue the cryptographic quotes, which then can later be verified. And yeah, so this is very important for the remote attestation procedure. And now the fundamental challenge with these commands is that they are executed on the host system, but we do not trust the host system. So of course, when we build and launch the VM, we can make sure that everything is correct. But how can we be sure that when we come back another day, that the host hasn't shut down the VM and started a new VM that looks like ours, but without the encrypted memory or without the code generation or with some other backdoors like monitoring socket or interactive terminal? How can we protect against these? Well, for building the VM, it's quite obvious. We do not build the VM on the untrusted host system, but we build the image on trusted systems and then transfer the image to the untrusted host. For launching the VM, it's more complex. We need to rely on a fully automated boot that does not require any manual input, because any manual input could, by one way or the other, also be read on the host system. So we need to make sure that the entire startup procedure, including remote attestation, happens during the boot procedure. And then, here comes the clue, we actually verify the integrity of the boot procedure itself via remote attestation. So this will be then included in the certificates and this cryptographic proof that we can verify on our trusted hardware. So to give the full picture, we start on the trusted environment where we build the VM image. This is our reference. This is the version of our VM that we trust. But of course, we don't want to run it on our hardware. We want to run it on the rented hardware. So we transfer the image to the untrusted host where we launch it. When we launch it ourselves, we can, of course, make sure that all commands are correct. And then the boot starts. And during the boot procedure, inside the VM, the TDX quote is generated. And the TDX quote kind of contains a fingerprint that tells us about the runtime state. And this quote is then signed by the hardware key and sent to our verifier on the trusted environment again. And here on the verifier, we can first, of course, verify that all certificates are correct. So we can verify that the cryptographic problems are, like the cryptographic proof is correct. But then we can also then combine the fingerprint from the quote with the fingerprint from our reference hardware. And that way we can make sure that the boot procedure that is part of this fingerprint is really the procedure that we intended. So after this bootstrapping, we have verified the integrity of the VM. And now we know, okay, this VM uses encrypted memory. And about the importance of encrypted memory, we'll hear in a bit.
Actually, the question is, did we test all this stuff? Short answer, yes. And it was quite a lot of fun. So suppose you have the following setup. You have an API server, an LLM server that accepts via some completions API a prompt. And this prompt is stored in the memory, of course, and after that it's sent to the LLM model. And the question is now, can we somehow read this prompt from the memory? And this is actually quite simple. As you've seen, there's this hypervisor layer, and actually a host, so a user on the host, can dump the guest physical memory. For instance, using the monitoring interface of QEMU and simply dump the complete memory. And as you can see here, those are the two cases. In case TDX is not enabled, you can basically find your canary prompt. And if TDX is enabled, meaning the CPU memory is encrypted, you simply find no matches. So actually, this works quite as intended. And of course, the key that is used to encrypt the memory is not accessible from the host system. That's the key point, of course. Now, when it comes to VRAM encryption, NVIDIA CC, things are a bit differently, to phrase it like that. Because this is how VRAM is actually accessed. As you can see here, this is the standard PCIe base address register approach, how you can dump memory. And in order to find the needle on the haystack, because we're dealing with B200 clusters, you've seen 180 gigabytes of VRAM, this takes quite some time to find the needle, right? What we did, so we wrote a small CUDA program that fills the complete VRAM basically with a canary string and see whether we can find it in the memory dump. And then, again, we save one random gigabyte of the VRAM and search for the canary string. And as you can see in the first line here, if confidential compute is not available, you find the canary string all along in the memory. And if confidential compute is enabled, you find no matches. But what is interesting is the complete binary file contains only zeros, which is interesting. You don't even see the ciphertext. So what you actually see is a mechanism that protects the host from reading the complete VRAM, and you simply get zeros at the end of the day.
You might remember the slide I showed you a couple of minutes ago, and by now we've talked about the data and use part extensively. Thank you, Marcel. But we still have to talk about the other parts. Why? Because just you enable Intel TDX doesn't mean you can just forget about these. So let's talk about these two things and how they interact with this Intel TDX setup. So first of all, we're in a Linux system, right? So naturally, you would encrypt your disk with LUKS, and that would be the end of the story, because when your laptop boots with encrypted LUKS, with encrypted disk, you would just type in your password, and that would be it. But the situation here is a bit different because your VM that you started always sits on top of the untrusted host, so you can't just type in your password because it can be easily leaked. Marcel also tested that. So what do you do instead? It's something also Benjamin mentioned before. You need to make this procedure not a manual procedure, but a fully automatic one. How do you do that? And this goes basically to what Benjamin said, just in a bit more detail. So when this VM boots, what happens in your Linux system first is not your usual operation system is starting, but another tiny Linux, if you want, is starting, that sees the encrypted disk. This tiny Linux generates your signed quote, your signed fingerprint, sends it to a remote verifier. This verifier checks this fingerprint against the known fingerprint that was measured before on a trusted hardware, and if everything looks good, you're happy with the result, you release the LUKS key and unlock the VM, and then your real operation system starts. That's about disk encryption. Now about the connection to the verifier, because again, the argument is this is not really trustworthy, the connection at first, because you again go through the untrusted host system. So what do you do now? Or what do you want to achieve? Well, you want the verifier to authenticate against the TDX VM, the confidential VM, but you also want the confidential VM to authenticate against the verifier, which is to say you want to have mutual TLS. So what do? So your VM starts, and as a first step, what you do is generate a client key pair for the mutual TLS. And now comes the interaction with, the important part, the interaction with TDX. Namely, this TDX code, this TDX fingerprint, also has a custom field. This is, I think, 64 bytes long, so not very huge, but you can put in custom data that is also then signed by the hardware key. So you put in a key, a hash of your client public key, send it via mutual TLS to a verifier. The verifier still does the things it has always been doing, but now in addition, what it does, it checks that the mutual TLS connection was initiated with the public key that is also part of the TDX code. And in that way, you now protect both the client and the verifier in the connection and prevent man-in-the-middle attacks through the host system. That's all I wanted to say about mutual TLS, but of course, that's not the only connection we care about.
Yes, now you have this confidential VM. Everything is safe, everything is nice, but doesn't do anything useful, yeah? Because, of course, you want to process workloads. That means you want to process input, you want to generate output. And you want to embed, so to speak, this VM into your infrastructure. In our case, we use a Kubernetes cluster for that purpose, and actually the confidential VM then joins the Kubernetes cluster as a Kubernetes node. But now a question pops up. I mean, you have this confidential VM, this Kubernetes node, but you have also other nodes, and you have a lot of errors, a lot of data that flows between those nodes. What about this traffic? And more precisely, if you look at the details of how this is implemented, of course, the wire is not protected, yeah? I mean, the network interface within the confidential VM is also visible on the host, apparently, yeah? Because the data somehow has to flow via the wire, so to speak. So a privileged user at the host could simply sniff whatever they can observe on the network interface controller. How to resolve this problem? Actually use encryption, which is not so surprising. But how do we do that in detail? So we use Cilium as a CNI plugin for our Kubernetes cluster. And Cilium comes with a feature that enables WireGuard encryption between the ports. And this is actually what we use. But what do we achieve? So let's go through the scenarios that we have. We have traffic from port to port that could be either cross-node or on the same node. If it's on the same node, then this is rather easy because the traffic does not leave the VM, and so everything is secure. If it is cross-node, Cilium kicks in with WireGuard and everything is protected. There's one thing to note, however, namely, if the port is in the host network, then this WireGuard tunnel does not help at all. You could basically observe the raw traffic there. This is the case, for instance, for Node Exporter and for several other ports that you might use. Apart from ports, you also have services, of course. And if you have a node port service or load balancer service in your cluster, then again the question, if it comes from if it exposes the service inside the cluster, luckily WireGuard kicks in because this Cilium EBF intercepts the traffic. But of course, outside the cluster, you see plain text TCP again. And outside the cluster does not necessarily mean internet. Yeah, you could think of your infrastructure in your private network, and you have some service that basically calls services on your Kubernetes cluster, and this needs to be encrypted by other means. So basically, this comes to the golden rules, so to speak, of network encryption. First of all, if possible, stay out of the host network. For Node Exporter, this is not so critical because it basically emits metrics that you can anyway observe on the host. But there are other ports, like the kubelet, for instance. And the kubelet is actually a reference model because all the communication is TLS encrypted. And if you have some external facing services, and I suppose you have, because otherwise you cannot process any input, make sure that you deploy any means of TLS encryption. Now, a small recap. So what did we observe until now? You've seen basically the way we build the VM image on our trusted Intel CPU server, store some reference values, and then the confidential VM on the untrusted host boots up, creates the TLS key pair for the mutual TLS, generates the quote, and sends it via mutual TLS to the verifier. The verifier does what the name suggests, verifies that everything is correct, and calls the key broker to release the key to decrypt the encrypted disk. This is exactly now the point where all the stuff that is encrypted on the disk can actually launch. For instance, you can join the Kubernetes cluster, yeah, and all the certificates and everything is secure within the virtual machine that has been proved to be trustworthy. But now, how does this look like in detail?
Yes. Thank you. So up to now, we've talked about this fingerprint very abstractly, and I want to take the time to just show you how this looks like in a bit more detail so you get a feeling. So first of all, how is this quote generated inside this confidential VM? This quote is generated through the Linux Trusted Security module, which is, well, it sounds very fancy, but in the end, it's just a very simple command. So what you do, you take some inputs here, just 0, essentially write it to a file, and what you get back is a byte string. That's basically it. Now, if you parse this byte string in accordance to the Intel specifications, you can get back some very interesting fields. So let's go through some of them. First of all is the TD attributes. TD stands for trust domain, and in this case, it just tells you that the VM is not in debug mode, which is of course important because a confidential VM that is in debug mode can leak memory to the host system just like an ordinary VM. Second thing is the report data field. This is the field I was referring to earlier when talking about mutual TLS. This is where you can put in custom data. So here it's just 0 because I inputted just 0. Then, maybe more importantly, there are fields called MRTD and RTMR0 to 2. MRTD stands for, I think, Measurement Registry Trust Domain or something. But what it measures is basically a hash of the firmware code and also the initial memory states of the virtual VM. The second one is about the virtual hardware environment. So for example, if someone came and stole your GPU from the VM, you would see it there. Then there is a field about the OS loader and partition table. And finally, there's a field about the Linux kernel and the initram file system. And this is exactly, remember the slide on the Lux encryption? There was this initram file system that unlocked the encrypted disk. And this part was necessarily unencrypted, but this field now guarantees that it has not been tampered with. So the initram file system is not a secret, but you would know if someone manipulated it. And finally, what you see at the bottom is the certificate chain of trust, starting at level 0 with a certificate that is bound to your hardware configuration, and it leads all the way up to an Intel root certificate. And in sum, this then guarantees the integrity of this TDX code. Now we've been talking extensively about CPUs and Intel TDX, but we should also talk about the GPU, because there is a corresponding way of doing things. So you could play the same thing. You could generate a GPU quote, a GPU fingerprint, send it to a remote verifier, they verify it, they send it back, all good. Or you could do something different, because now we are in the stage in talk where we are trusting the VM, because already booted, you got attested, so everything is good. It's like your own OS. So what you could do instead is you run your verifier inside the confidential VM, and this verifier now checks stuff like GPU driver, firmware, hardware state, and so on and so forth. Then it also signs it with a hardware key, now not from the CPU, but from the GPU. Verifies it. If all is good, it sets the GPU into a ready state. I will show you what this means in a bit. And then once it has done that, it could report back to a trusted environment like your Kubernetes cluster and say, hey, I'm ready, please give me some work. This is an example of such a GPU quote that has been generated with NVIDIA Test, which is a tool from NVIDIA. And similarly to the TDX quote, it gives you information about the BIOS, the driver, some certificate chains, and so on and so forth. So where are we at? So now we booted the VM, we trust the CPU, we trust the VM, we trust the GPUs, but still the VM is not yet ready for workload, because there's one small detail one has to do in the end, namely one has to unlock the GPUs. So in this state, when you booted your VM, your NVIDIA SSMI command that's shown here will show you that the GPUs are not ready, so they will completely block. You can't do anything with them. But once you've attested your GPUs and you know that they are in a good state, you can run yet another SMI command to unlock the GPUs. And now we are finally in the state where our VM booted and they are very ready to serve some LLMs.
Yeah, let's go back to the beginning. What was our initial goal? We wanted to run confidential inference on our rented hardware. And not just any inference, but some state-of-the-art model like GLM 5.1, which is a very large model. So it needs to run on several GPUs. And typically, we run these models with inference engines like VLLM as Kubernetes containers. And we have already seen how to integrate a confidential VM into our Kubernetes cluster. So this is great. But what we would also like to verify is if the NVLink connectivity between different GPUs on the same server actually still works. Because this model needs several GPUs, and it needs to have a lot of communication between the different GPUs. And if the NVLink was broken by the VM, then we would have much worse performance. And luckily, when we check, this is the topology. And you see for every pair of GPUs, there's an entry called NVLink, basically. So this just confirms that we did not break anything, so NVLinks should still be available inside the VM. And now we have all requirements. We can actually run inference inside this confidential VM. So it is compatible, it works. Unfortunately, there's still a small fee attached to it. So the performance is not as good as without the encryption. And here you see the comparison in yellow, the output throughput without TDX, and in green with TDX and confidential compute. And the difference is about 20% in output throughput, which is not ideal, of course. So some of it is because of the encryption overhead. So any communication needs to be encrypted, and that really adds up. Another part might be just because of lack of optimization. So inference in general is a highly optimized technology, and it is really optimized for very specific hardware. And it could be that by enabling confidential compute, some hardware features, some GPU features are not available or available in some very specific flavor, and the optimization by VLLM just expects different hardware features, and it just does not like max out the available hardware. So there is some hope that in a few months, maybe some inference engines will really focus on inference in confidential environments, and then we will also bring these two lines closer together. But on the other hand, we wanted to have confidential inference. And confidentiality is something that you can't really outweigh with speed, right? So this technology enables new use cases where you can make use of hardware that you do not own. And this is really a great benefit. And that brings us to our summary. So what have you learned? First, Intel, TDX, NVIDIA Confidential Compute are two techniques that provide verifiable proofs of integrity. This is really, really important. It's a milestone. You no longer have to trust the provisioning layer. You no longer have to trust the cloud provider. You no longer have to trust any contract and promises in the contract. But you can really verify the integrity on your own. Second, while TDX and CC are very powerful technologies, they only cover so much. And you really need to also consider data in transit and data at rest. You need to use looks, MTLS, WireGuard, and so on to protect the entire chain. So it is not sufficient to simply take a TDX-compatible server, launch a VM, and say, well, now I'm safe, because you entirely missed out the remote attestation, so it's like worthless. So there's really a whole lot of other complexity that needs to be added in order to achieve this confidentiality. And third, the good news, you can run confidential inference on this hardware. It works. There is some performance fee attached, as I said, but for us, it is not really important because we already have a lot of own GPUs, right? But there are, of course, many clients who are shy of buying their own GPUs and maintaining their own clusters and so on. So they could, in principle, go to a cloud provider that provides like TDX and CC compatible hardware, set this thing up, and then run confidential AI services on rented hardware. And this is really a door opener. And I think it's especially valuable for like smaller companies who can't really invest into their own GPU cluster. That's it. Thank you.